This is Andraž Repar, and he'll be discussing good examples for terminology databases in the translation industry.
So, hello. So, as said, I'm Andraž Repar, and I'm a student at the International Postgraduate School at the Jožef Stefan Institute in Ljubljana in Slovenia. But I also work as a quality manager for a translation company called eLex, which is also based in Slovenia. This is our logo up there. eLex means eagle in Irish Gaelic. That's why there's an eagle in the logo. So, and Senja, the co-author, she's a postdoctoral researcher at the JSI Institute. So perhaps some of you are wondering what's a quality manager from a translation company from Slovenia doing here at the Lexicography conference. Well, eLex has been on the market for quite some time, for more than 20 years. And if you remember the first keynote speech on Tuesday, we heard a bit about the technological changes and the disruption they're causing in the translation industry. And we have witnessed those changes, firsthand, and we have experience with them. And what I think it's important here to say is that the technological changes in the translation industry are not a recent phenomenon. This industry was probably one of the first to undergo what's called the digital transformation. More than 20 years ago, or 30 years ago, a piece of technology came to the market called a translation memory, which essentially revolutionized how the translation industry works. So this is essentially a database of all translations, so everything you translate gets into this database, and when you get the same or a similar sentence again in the future, you don't have to translate it from scratch, you just recall it from the database. And this changed how translators are paid and how translation agencies charge their clients and so on. So, and there have been many other technological advances and disruptions over the years. For example, machine translation is very popular now. But one thing that hasn't really changed from 20 years ago is how terminology is handled in the industry. You still have to do, if you want to do properly terminology work, you have to do it manually. So you have to collect the terms, you have to collect the definitions. So this is all manual work. Despite having all these translation memories, which are quite big and quite large and have lots of useful information. However, in our experience, terminology is one of the biggest issues when it comes to translation quality. And it's not just us. For example, SDL, which is one of the largest translation software providers in the world, made a survey last year about translation quality, and they asked about 2,700 participants who were language service providers, freelance translators, and translation buyers. They asked them for one of the questions was, what's the top cause of translation rework? Which means when the translation is not good enough, it has to be redone. So we translate it again from scratch. And the number one answer that came back was inconsistencies in the use of terminology. So clearly, there's something missing in the market. So in 2015, we decided to do something about it ourselves for our own internal processes. And we started working with the JSI Institute to develop our own terminology management, terminology extraction system that would help us in our work. So it's basically, on the one hand, it's a database for terminology, for terms, and the core component is a terminology extraction process, specifically a bilingual terminology extraction, which utilizes these translation memories that are so common in the industry. And we also thinking about extracting additional information such as definitions and domain extractions. And then later on, we found out that we need to also include good example extractions, and this is what this is why I'm here today. So let's look quickly at the outline of my talk. So first, I'm going to introduce what's the problem with good examples. And then we're going to talk a bit about the data set that we had and what we did with the data set and how we decided to look for a good example, which is to use machine learning. I'm going to talk about the features and some results, and also provide at the end some conclusions. So it turns out that, finding a good example is a surprisingly difficult task. At first, we thought we didn't think we're going to need something like this because we thought we had all these examples. Surely it must be easy to just quickly pick one or two and have and that's it. But it wasn't that easy, and then we started to look into the literature and found, for example, this definition of a good example, which was kind of our starting point for this task. And then we went from here. So what we did for this experiment? So we took one translation memory that we had, and now translation memory, as I said, it's essentially a bilingual parallel corpus. The good thing about this being an old technology is that it's fairly standardized, so almost all translation software tools support, at the very least, this translation memory exchange format, so our solution is compatible with almost all tools in the market. And I think it's important that I stress here that we are working from a bilingual perspective from the start, so our good examples are actually pairs of good examples in the source and target language. So if a good example is only a good example if the English sentence is a good example and the Slovenian sentence is also a good example. So I think it's a bit different to what the other people are doing. So as I said, we took an English-Slovene translation memory with the content was a financial domain, so equity funds, annual reports, and so on. And we did some pre-processing, we removed the tags, we tokenized the sentences, we performed part of speech tagging, we lemmatized them, and so on. And then we extracted terms on both sides of the corpus, so monolingual extraction from the English sentences, and then a separate monolingual extraction from the Slovenian sentences, and then we manually aligned the terms so that we get term pairs and the corresponding sentences where these term pairs appear. Then we gave these sentences to two annotators who split the work and then manually annotated 1,332 sentence pairs as either good or bad examples of the term. And we ended up with 362 good examples and 970 bad ones. And then so this was our starting point, our data set, and we fed this into a machine learning algorithm. And because we had a binary target variable, we performed binary classification. Some related work, briefly, when we constructed the features, which I'm going to talk about a bit later, we leaned quite heavily on this first paper, which is GoodX for Slovene, which is I think quite well known here. And the second one I'm mentioning is because it's in a way similar to what we did with three important differences. So instead they also use machine learning, but instead of classification, they use regression. And they work on monolingual example sentence, whereas we use sentence pairs, bilingual examples. And they use 4 categories of good examples, so whereas we use just 2. So these are the important differences with this paper. Here's a quick example of the examples. The first one was annotated as a bad example. The second one was annotated as a good one. And this was done for all 1,332 examples. Here's a list of features that we used. Altogether, there were 20 features. 15 of them were numeric, which means that the values were numbers. For example, the length of the sentences or the position of the term in the sentence. 3 of the features were binary, which means that the values were either yes or no, so just 2 values. For example, whether the sentence starts with an initial capital letter and ends with a final punctuation mark. And 2 of the features were nominal, which means they didn't have numbers for values, they had actual values, like the case of the term in the target sentence. So we calculated these features for all the examples and fed the data set into the Veka data mining tool, which is a well-known data mining toolkit. And we use these 5 algorithms, which are all available in Veka. So naive Bayes, a decision tree algorithm called J48, a k-nearest neighbor algorithm, a propositional rule learner, a support vector, and a support vector machine. And then we also did some additional tests with discretization of the data, which is when you have numeric values of the value. You group the numeric variables into sort of bins. So instead of actual numbers, you have different groups for values. And finally, we also used for some configurations the feature selection, which again, this is useful because it reduces the number of features. So we started with 20, but after feature selection, you only the ones that are the most informative for the classifier remain, and in most cases, we were left with quite fewer features, which is useful from a performance point of view. And here are some results. We did tenfold cross-validation, which is the standard cross-validation evaluation technique in machine learning. The first thing that should be probably noted is that we have an unbalanced data set, which means that we don't have a 50-50 distribution, but there are more bad examples than are good ones. So if you look at the last column, accuracy, if we were to take the entire data set, so all 1,332, and classify them as bad examples, we would get an accuracy of around 73%. So any classifier that performs worse than this is probably not a good one. And in this example, and so here, so this is probably not a good classifier because it performs worse than if you just take everything and put it into the majority class. This also means that if we are to randomly select one example from our data set, we have about 1 in 4 chance of getting a good one. So we use these standard measures of performance. So in terms of recall, for example, naive Bayes performs quite well. What this number here means is that, so these are values for the positive class, for the good example class. And what this means is that naive Bayes actually gets almost all of these good examples, but it also gets a lot of noise. So a lot of misclassified bad examples as good ones. So so naive Bayes is not really a good classifier for these tasks. On the other hand, in terms of precision, this configuration of the decision tree algorithm proved to be the best with an 80% precision. And this means that using this classifier, we have about 4 in 5 chance of getting a good example. So that's quite a bit better than just randomly picking something out. Yeah. A bit further into precision. So giving the specific task that we have is, we have lots and lots of these examples, but we only really need 1 or 2 or maybe perhaps 3. So we're not really interested in recall because we want a classifier that will be very precise, that will only return those examples that are actually good ones, but it doesn't really matter if it doesn't find all of them, all 362. So even if it just returns 10 of them, if 9 of them are correct, then this is a good classifier for our task. So here's a ranked list of all the configurations. So we can see that the decision tree, so the J48 classifier seems to be the best one for this task. This propositional rule learner JRIP also seems to be quite good. The k-nearest neighbor algorithm down here is a bit worse, but still good. So support vector machine is again a bit worse, and naive Bayes doesn't even come on this list. So yeah, maybe just a bit about the most informative features. So we performed, as I said, we performed feature selection, and the number of features was significantly reduced. So except for the support vector machine classifier. So for all the others, the number of features fell from 20 to 3 or 5 or 6. So there were just a few features which were informative enough for a good model. And the following 3 are found in 4 out of the 5 models. So this could be kind of considered the ones that are the most important for this data set. And now I'm coming to the end. So what we have found out is that all classifiers except naive Bayes have improved over the majority class classifiers, so are kind of suitable for this task. And in terms of precision, the best one appears to be the decision tree classifier, the J48, and the best configuration would allow us to get a good example in 4 out of 5 cases. So that's quite good. We also discovered that discretization and feature selection did improve results, and there was also a significant reduction in the number of features. So all in all, I think machine learning seems to be a feasible approach to finding good examples. We also have some ideas for what we want to do in the future. Of course, we have to test this on other domains, not just the financial domain, and also other languages. Now, the majority of the features that we have can be considered language independent, but some of them are not, so there would have to be some adjustments made, but I think the majority of them could work for a number of languages. And we also thought about some new features that could improve the performance. For example, looking into the specific sequences of word types of good examples, or we could also look into word frequency, relative word frequencies of words in good examples, so we could compare the frequency in this specific corpus that we are working on with the corpus of a general language, and if this would then give us an indication of how domain-specific a word is, and if a good example would contain too many domain-specific words, it would probably not be a good one. So with this, I'm at the end of my presentation, so thank you, and if you have any questions, please ask.
For the video.
Okay. Thank you very much for your presentation. This is interesting stuff that needs development a lot. I wanted to ask you, were you taking into account the directionality of the translation?
I mean, yes, we do. I mean, the translation memories are usually one-directional. So in this case, English is the source language, Slovenian is the target language. So if we were to use this in a professional translation setting, we would probably make a different term base and a different with different good examples from a different translation memory if we were working from a Slovenian into English direction. So yes, that would be, but that would be at the level of the data.
Okay. Am I allowed to have a second question?
Sure. Sure, we have lots.
Sorry, just very briefly. In the judgments, expert judgments of the good examples and the bad examples, did the judges have any training? Were they looking only for the translation quality of the term?
No, we gave them, we gave them some ideas. We gave them this definition. So this, they received this. And we talked, they didn't get the precise specific instructions of what is a good example, how long it should be, but that's not really the point, because in machine learning you annotate something and then the algorithm tries to find a pattern. So they did receive this, and that was the starting point.
Okay. Okay. You did not make a distinction between examples for language production or examples for language reception, because they're
No, I mean, this is meant for, I mean, this is supposed to be used, this was to be, I mean, will be used in a translation production environment. So this would be something that translator would see that would help him understand the term. So this was the perspective.
okay. So, but although understanding the term is more language reception, and production is being able to use the term in context, in with the correct collocations and phraseology, right?
Yeah.
So, yeah.
Okay.
There might be a difference. Well,
Yeah.
thank you very much. This is anyway very interesting stuff. Thank you.
All right. Any other questions? No? All right. Well, thank you very much.
Thank you.
Really interesting.